Hey students, in this video we're going to talk about the inverses of functions. So the first thing that we're going to do is we're going to get a few definitions, some steps, and then a concept about graphing. So the definition of an inverse is we say a function f of x has an inverse, and we notate that f to the -1 of x if for every point AB on f of x, BA is on the inverse. So all the points from f of x swap on the inverse. So how we find an inverse is we're going to swap the input and the output. We're going to switch the x and the y's, and we're going to solve for y. What this does transformation-wise, inverses are a reflection over the line y equals x. Y equals x. So just to kind of drive that home, talking about the swapping of points, let's say I wanted to highlight really quickly on the original function. The original function is graphed in red. And if I wanted to talk about the point on the x-axis, this is the point 1, 0, then what that means is that there's going to exist a point on the inverse function that is 0, 1, and that is true here. If I plot this point, we have the point 0, 1. And so this is always going to be true. A function and the inverse, those two values will always be swapped. Okay, so our instructions for this are to find the inverse of a function f of x equals the quantity x plus 2 cubed plus 3. So our steps for finding an inverse are to first swap x and y. Well, it's important to understand that f of x is the same thing as the output of a function, meaning it's the same thing as the y value. So I'm going to rewrite my equation with y. Then I'm going to swap my input and output. So I'm going to swap the x and the y. And this is what is called the inverse equation. This inverse equation is what is called the implicit form. We call this implicitly defined because the output is actually inside of the function and the input is outside of the function. So this is not function notation. We want the output to be alone by itself in order for it to be considered a function. However, you can graph this inverse equation and see that this equation is the inverse of this function. Let me show you the graphs. Okay, so I've got the original function graphed. I have the inverse equation graphed, and then I have the graph y equals x also graphed as well. So you can see the original function, the reflected inverse, and the line that it's reflected over. Desmos is great because it doesn't need to be in y equals in order to be able to graph it, but on your handheld calculators, it is required to be in y equals. So a lot of times what we'll also ask for students to do is to solve for y in the equation. So let's talk about how we're going to do that. To solve for y, we need to undo the operations that are happening to y. We want to start on the outside and work our way towards the y. So the first thing that I'm going to do is I'm going to subtract 3 on both sides of my equation. Subtracting 3 on both sides of the equation will get rid of the 3 and put it on the side with x. To get rid of the cube, I'm going to do the cube root on both sides. Again, just doing inverse operations the same way you would solve an equation. The cube and the cube root are inverse operations, so similar to the addition and subtraction of 3, they'll cancel each other out. And the last thing that I'll do to get y alone is I'm going to subtract 2. When I subtract 2, I want to make sure the cube root kind of acts like a set of parentheses. So that's a group in and of itself. So when I'm writing my final answer, it'll be the cube root of x minus 3 minus 2. The 2 is coming after the cube root has been applied. And this is the equation that represents the output of the inverse. And we use this to say that this is equal to f inverse of x. This is the function's inverse in function notation. So this is the inverse function. Because it's the inverse function, we can also graph it. And you'll see that it's the same graph as the blue. You'll see that it lies perfectly on top of the blue line. So again, two different types of inverses. There's what we call the inverse equation, and then there's the inverse function. Again, usually we always ask for the inverse function, so it is important to be able to solve for y to find the function. Okay, pause the video and see if you can try this example on your own. You've got the function f of x is equal to negative 2 times the square root of x minus 3 minus 2. Okay, to solve for my equation, the first thing I did was replace the function notation f of x with the variable y, which we also use often for the output of a function. I swapped my x and y to create my inverse equation. And then to get it in function notation, I solved for y. So the first thing I did was undo. Whenever you're solving, you want to follow order of operations in reverse. So undoing subtraction using addition, undoing multiplication using division, and then the square root is acting like a set of parentheses, so I'm undoing that groupage by squaring both sides. And then once I undid the square root, I had this minus 3, so I'm going to undo that at the very end, going back to the beginning or the end of order of operations, adding 3 to both sides. And here's my inverse function. I do think it's worth taking a look at the graph of these. Some really interesting things happen when I graph the inverse function, the original function, and the inverse equation. So I'm going to show you that. Okay, first, originally, I have graphed the original function. It's this negative, a negative square root function. So it looks like the square root function, but it has been reflected over the x-axis, and it's been vertically stretched and shifted again. So this is my negative square root function. Now I'm going to show you the graph of the inverse equation. So again, we're talking about this reflection over the line y equals x for every point on the inverse. Like for instance, here's negative 2, 3. There's the point 3, negative 2 on the original. So all of those points swap. And then what I want to show you is the graph of the inverse function. So the inverse function in this case doesn't quite look like a true reflection. Whenever you, and this sometimes happens when you're switching function types, right? The original function was a square root function. The inverse function is a square function or a quadratic function. And because of that changing of types of functions, there's still a reflection happening here. So these points are still being reflected. So there's still the point on the original function, 3, negative 2, and 2, negative 2, 3. And there's also, we could find another point for negative 4. And I can also find the point negative 4, positive 4 on the other function. But again, sometimes what happens is the shape of these functions is creating an extra piece. So this part of the function is the reflected part. And then because of the quadratic symmetry, there's a second part to that quadratic function. This doesn't create a ton of issues for us right now, but it is important to know that parts of this function, So this part is being reflected here. And then because we're creating a quadratic function, we're getting a second piece to that function because of quadratic symmetry. Okay, so that's it for this problem. Again, just worth showing up that sometimes when you switch functions, you are going to see some additional pieces to your inverses or missing pieces from your inverses. Okay, the next example that we're going to do is a rational function or a function that's a fraction. Sometimes these are a little tricky, so I'm going to talk through how to find or how to solve for y here. So I have the function f of x is equal to 9 over x minus 2. So the first thing I'm going to do is start by replacing f of x with y. And then to actually create the inverse equation, I'm going to swap my input and output. So here's my inverse equation. But in order for it to be a function, we need to actually solve for y. To solve for y here, I need to get the group out of the denominator. I have a y minus 2 in the denominator, and so I need to undo that. So I'm going to multiply both sides by y minus 2. The division of y minus 2 and the multiplication of y minus 2 cancel, leaving you with just 9 on the right side. Then to get y alone, I can distribute my x, or the goal is to get y alone, so I can divide both sides by x to move the x to the other side. And then my last step to get y alone here would be to add 2 to both sides. Won't spend a ton of time with this, but I will show you the graphs. You can see that the original function and the inverse function are inverses of each other. They are reflected over the line y equals x. And notice that an inverse of a rational function is yet again another rational function. So there's no strange cutting off of the function because we're keeping the inverse and the original function and the inverse are in the same family of functions. Okay, the next example that we'll do is one where you have multiple inputs. Sometimes this can be tricky when there's a rational. So to start this, again, I'm going to replace my original function is f of x is equal to 4x plus 5, all divided by x. So I'm going to start this by replacing y and swapping my input and output. Make sure when you're swapping your input and output that the x is replacing y and both x's are being replaced by y. So to solve this one for y, we want to get y alone. So the first thing that we're going to do to get y alone is similar to the last problem. Anytime there's a rational, I'm going to get rid of the fraction by multiplying the denominator to both sides. And then I need to get all my like terms on the same side. So any term that has a y, I need to get it on the same side of the equation. So that way all my y's are on one side. So I have xy on this side, I have a 4y on this side. So I'm going to subtract 4y from both sides to get my y terms together. Once the y's are together, then we can use the technique of factoring to factor out a y from the left side. Both of these terms on the left side have a y in common, so we can GCF factor a y out. I can check my work, right? Y times x would be xy, and y times 4 would be, or negative 4 would be minus 4y. So I've just pulled the y out of both terms outside of a set of parentheses. My last step to get y alone is y is now being multiplied by the factor x plus 4. So I'm going to divide both sides by x plus 4. And I said plus 4, but I meant minus 4. And this is my inverse function. Just a reminder, we can notate this by saying f to the negative 1 of x. Okay, the last thing that we'll talk about in this video is that composition can be used to verify that functions are inverses of each other. So a function f of x is a function and its inverse is f to the negative 1 of x. Then the composition of f with the inverse inside of f and the original function inside of its inverse will always cancel each other out, leaving you with x. So taking a look at a quick example, we're going to let f of x equal x squared and g of x equal the square root of x. So if I find the composition, for instance, if I find, we know that the square and square root are opposites of each other, which means they are inverse functions of each other. And if I find f of g of x, meaning I'm placing g of x's equation into the input of f of x's equation. So I've got g of x in red, that's going inside of the quadratic function. So I have the square root function being squared, and we know that the square root and square cancel each other out. So I'm only going to be left with x. This shows that the f of x function and g of x function are inverses of each other. I could also do this the other way around. And the square root of x squared, again, the square root and the square cancel, leaving you with only x. So as long as when a function and its inverse are composed, you're only left with x, then the two functions are inverses of each other. So it's a great way to check to see if two functions are inverses. Let's take a look at one more example. Use composition to show that f of x, 2x plus 2, and g of x, 1/2 x minus 1, are inverse functions. So we're going to use composition. First, I want you to find f of g of x. And since composition is review, I want you to pause the video and try this on your own. When you compose putting g inside of f, distributing and combining like terms, you should have gotten just x. And then we'll also check g of f of x as well. Pause the video and try this one on your own too. And again, you should have just gotten just x. Because this is true, when you compose f of g of x and g of f of x, you get x both times. This verifies that f and g are inverses.